Good evening, everyone. Uh, we'll wait for a couple of more minutes and then we'll start. Okay, then I think we'll start now. Uh, Good evening, all. Uh, my name is Umair Hussain. I'm a PhD scholar at the Department of Mechanical Engineering at IIT Madras, and I'm here to take your doubt session for the course Finite Element Method, Variational Methods to Computer Programming. So it's a 12-week course, and I think uh, till week 9 it has been uploaded, I guess. So we are lagging a little. So I had to take 2 weeks off due to some conference, and so we'll continue the same. So to also to cover up that part, I'll be taking one extra class this Sunday. So yeah. So so far in the course we started with the basic principles in variational methods, and then we use the concept to get the governing equation for any physical problem, and then we started with the basic steps in the finite element method. So yeah, in second week we covered the basic steps involved in solving any FEM problem, and then we started with the basic 1D FEM problems. We covered a little bit of those basics, and found and formed a foundation on how to use the FEM in 1D, and how to formulate a computer program also for that. And then we did some examples on structural problems. So we did problems on 1D bar elements, and then we did some problem on truss elements, and then beam elements. Finally, the discussion was concluded by a generalized frame element problems, and I think, yeah, that was the end of the 1D FEM part. And then last in week 6 we had to start for the so after 1D we had to start basic 2D problems, and then for that we need some foundation. So in week 6 we covered basic I think calculus part, and initial notation and all that, Gauss divergence theorem. So until last time we covered that part, week 6, and now we're actually starting 2D FEM problems. So we'll first start with the scalar field 2D problems. So can anyone tell me what's so special about scalar field? What is a scalar field problem in 2D FEM? Any guesses? You can either type in the chat box or unmute yourself and speak. By the way, I hope my audio and screen are fine. Audio is okay and screen is visible. Okay, thanks. Okay, so in scalar field problems, we define only one uh, single unknown or single dependent variable. We solve for only one dependent variable in the entire domain. So we have some random. So we'll take some grid points. So we have some mesh. We have different nodes here. So at each of these nodes, we solve for only one variable. So we define only, say, u, the function of the space coordinates xy. Or it can be even be this concept can also be extended to 3D, but we'll start with 2D. So and opposite to that, we will later study vector field problem. So in vector field, there's a vector involved. So instead of just one variable, we'll have multiple. So for we'll have u x comma y, you can have v x comma y displacement in x, displacement in y. You can also have temperature field. So in vector field problem, there will be multiple variables involved or multiple unknowns involved. And as many unknowns are there, that many governing equation would also differential equation would also be there. So we start with a scalar field problem that is the simplest to solve in 2D, and we take up an example of the heat conduction in 2D problem. So in heat conduction problem, we only have a single unknown, that is the temperature field. So we consider 2D. So that means there is no variation of temperature across the thickness of the domain. So it's just in varying along across the 2D domain, and across the third dimension, there is no variation in the temperature. So if you remember that the strong form or the governing equation of heat conduction problem looks something like this, where this is the Laplace term, or we also call this a Poisson's equation sometimes. This is a Laplace term, and this is the sourced. This equation in general is known as Poisson's equation. I think if when source term is not present, then it is called Poisson's equation. Or you can say an inhomogeneous Poisson's equation. So that doesn't make much difference. So yeah, if we break the components, we'll have the equation something like this. So we break it down into x and y components. So there's a second derivative of temperature with respect to x and then with respect to y. So, like in any FEM problem, how do we start first? Anyone, any guesses? How do we start solving an FEM problem? Finding shape functions. Uh, in general, you don't need to find shape functions. Anyways, we'll derive them as we're studying FEM, but usually you define, you discretize the domain into different elements, and based on the elements, you already know the shape functions or approximation functions. So we have to you can say we discretize the domain, and based on the type of elements, we choose a type of element and the type of approximation function. So it's basically a choice. And before that, one more thing we do is to find the weak form of the problem. That is more fundamental. So yeah, first thing is weak form, and in getting the weak form, uh, for how do we start it? We write the variation statement, or the we multiply the governing equation with the weight function and integrate it over the domain. So in order to minimize the error, or what do you call residual. So in last week we did study Gauss divergence theorem. So Gauss divergence theorem is an alternate to what we used to do integration by parts in simple 1D. So here, instead of integration by parts, it's a little more tricky in 2D or 3D. So we apply the Gauss divergence theorem to uh, to reduce the differentiability requirement. So here right now there's a this term has a second order derivative over it, right? There are two nebulas or two Del operators. So how do we apply Gauss divergence theorem is we it's a basic trick that I follow by you move this del operator over the weight function uh, in the first term, and second term you just remove this term del operator and take a dot product with the normal vector, and its integral should be over the surface area. So gamma represents the surface and omega represents the volume of domain. Plus, then our source term is left untouched because uh, there are no differentiability changes required on that. So finally, our weak form is of this form. This is something similar to what we had seen in 1D. Now, instead of single derivative respect to x, we have a del operator, or we have a gradient. So this actually means a vector dou w by dou x, dou w by dou y, and this also is a another vector dou t by dou x, dou t by dou y, and kappa is a constant. In this case, we consider constant. Usually, for some anisotropic case, this can also be it's actually a second order tensor in that case. So if we simplify this, dot product of these two vectors would be dou wx dou w. So we take the dot product. We'll have dou w by dou x, dou t by dou x, plus dou w by dou y, dou t by dou y. Now, next thing, we approximate using the piecewise polynomial or the whatever approximation function we are going to choose. So if you remember, we used to choose a set of shape functions or the approximation functions phi, and used to approximate like this tj pj, and similarly for the weight function we do the same approximation using the same set of since we are following the Galerkin method. So when we substitute these, we can write the integral on the left hand side in this form, and this would give us a matrix Kij, and we have our solution vector as it is. We can take it out of the integral, and since it is independent of the space coordinate xy, and then whatever is left on right hand side is the force vector. So this way we can get the our algebraic equations for the entire domain or the element. Okay, so this part is I think straightforward as what we did in 1D. So the new thing in 2D comes up when we describe discretizing the domain and define the approximation function. So now we have rather more complicated elements. So unlike in 1D, where we just had one choice, it's a line element every time. Whatever the domain, whatever it is, it's just a line at the end of the day. And so whatever element you're going to form will just be a line element. But in 2D or 3D, the geometry is rather complex. And to break it down into different elements, you have uh, a wide variety of choices. What kind of element you want to choose? You want to take triangles, you want to take quadrilateral, you want to take pentagons, hexagons. You can map with any kind of shape that you want. But in practice, we usually stick to two standard shapes, which are easy to for calculations and easy to understand. So usually we go by either triangular elements or we go by quadratic elements or quadrilaterals. That is three side three nodes or four side four nodes. So these are pretty standard elements that are used in most of FEM solvers. Can anyone tell me which of these two is better? Anyone has any opinion on this? Triangle is better. Why so? Why do you think triangle is better? It fits in perfect in curved edges. Ah, that is right. So you mean to say that rather complicated geometries can be very easily covered with triangles, right? Yeah, that is one good advantage of triangular elements. Is there any other advantage? Anyone else can think of? Number of unknowns would be reduced. That's not true every time. So you can just take this this is my square domain, right? these are my nodes. So either I take it as one single quadrilateral element or two triangular elements. At the end of the day, uh, I'll be solving for the four equations, right? For the four nodes. But you can argue that we'll have more number of elements, so uh, there will be more calculation involved. Per element, there will be total more degree of freedom, three for each. You can argue that. uh, Okay, okay, we can take that. But one important uh, advantage of triangular elements is that for many polynomial integration over uh, triangular element. Let me write this first. So there are certain general formula of double integral over triangular area. So if your polynomial is of this kind, which is mostly the case in our FEM integrals, there are based on these powers of eminence, there are direct formulas for that. So what this does it that it saves you the processing part of for numerical integration. You just have to give the formula directly to the solver, and it will solve the integral for you straight away. So there are many commercial software based on this. So that's why there are many software that prefer using triangular elements over quadrilateral elements. So it makes processing much faster. So any disadvantage of triangular element where quadratic element is better? Any guesses? Okay. So one thing in triangular is that for post processing for when you calculate the derivative of the solution, that is in case of uh, your equilibrium problem, uh, your strains and stresses would turn out to be constant. So that is one major issue with triangular elements. So quadratic elements would give you uh, m- somewhat better results, you can say, when you are calculating uh, further further order variables. I mean, for the derivative of the variable. So there you can say that quadratic element turn out to be giving improve better results for that case. And in general, we have for especially for your stress problems, stress strain problems, it is essential to do this post processing. So in that case, quadratic elements are better. But I think you are right. Most of the solvers we see triangular elements are being used. But there's one solver that I use. I mean, there's one library called Deal2 that I use, and uh, those libraries are built only for quadratic elements. There's no support for triangular elements. So I think I'm not sure why that particular thing is for that library, but that's that. Okay, so yeah. So here, so far we have in this week's lecture we have studied only triangular elements and how can we form the approximation function. So suppose we take any triangle with nodes 1, 2, 3. So if we want the approximation for each for the three of the approximation function for the element, there's we know that the approximation function follow this. pi equals to pi at sorry xj is always equals to delta ij. What does this mean? That if if we are calculating a fee for node 1, it would give value 1 at node 1, and at the rest of the nodes it would be 0. So yeah, that's how. So if we substitute, if we consider a general form of phi 1 of this kind, uh, we're considering a linear type of phi. And so why do we come up to this approximation? So firstly, we are considering only linear type of approximation function, and secondly, we need since we know the coordinates of three nodes, so we should have only three unknowns here: a not a1, a2. So if we substitute the coordinate values in this function, we'll get these three equations here. Similarly, we'll do for phi2 and phi3. We'll get three equations every time. So we can, if we merge these three equations, we'll get a matrix operation like this. So this matrix A here is multiplied to this matrix B here, and what we get is identity. So what does this tell about the relation between A and B? Any idea? What does this matrix equation tell about the relation between A and B? Any guesses? By the way, I think I said something wrong here. Number of unknowns will be reduced when compared to quadrilateral. So you said that the number of unknowns would be reduced in triangular elements, but there I showed that number of unknowns would be more for triangular element, right? Because consider that same square domain, you will have to break it into two triangles instead of one quadrilateral. So turns out that you'll have more number of unknowns for triangular elements. So that you can say is one more disadvantage of triangular elements and an advantage of quadrilateral elements. Now I thought about it in this way. I hope what I said was clear. Yeah, thanks. Okay, so if you look at this equation that two metrics are being multiplied, A into B, and what you get is an identity matrix. Identity which is all diagonal as one and rest of the elements as zero. So this is uh, true when B is equals to inverse of A. So you know that property of matrices, that if any matrix A is multiplied by its inverse, then we get an identity matrix. So it turns out B is just nothing but the inverse of A. So and getting A is not a complicated task. You know the nodes of the know the coordinates of the nodes of the triangle or the element. You can get the this A matrix, right? And then you just have to get the inverse of it. Then you whatever the inverse of the rows and column, the elements of the inverse of A would be, those would give you the these coefficient of the approximation functions. So that's how you can use this coordinate data to get the approximation function for any triangular element. By the way, this should only be valid for triangular elements, I guess. I don't think this trick, I don't see how this trick can work for any other type of elements. Anyways, so I hope this step is quite straightforward. Next, what are the some properties of these shape functions or approximation functions? Firstly, that they should be piecewise polynomials and should have C0 continuity. And then secondly, the combination of these piecewise polynomials should be continuous in the entire domain. And then third is these approximation function should be linearly independent. And fourth is these approximation functions should be complete. So a complete polynomial means it should, so if it's a first order polynomial, it should have all the term till first of who are of the order 1 to below that, or that means simply 0 here. So for if you're defining a first order polynomial, I read one here. So a first order polynomial should have zero order terms. So we can write p naught. It should have, and then it should have first order terms. So if it's just 1D, then this much is fine. But if it's 2D, then we also need. Okay. So same way, if we are defining a second order polynomial, so a complete second order polynomial should have a 0 degree term, first degree term, as well as second degree term. So that's what is complete polynomial. Okay, so now here we have done the approximation function part or shape function part. Next, in FEM, the next step is after solving the element level equation. The next thing is assembly. So I think I have discussed this part in one day also. We for generalized assembly process, we go through the technique of connectivity matrix. So I hope you all are aware about this step. And can someone tell me how do we form the connectivity matrix for this given domain here? For element 1, 2, 3, 1. That's right. 2, 3, sorry, 2, 3, 1. And we want an answer for 2, 2, 3. Is for element 2, it's 3, 4, 1. That's right. So yeah, that's easy way to get the connectivity matrix. And then the next less easy part is to do the actual assembly based on this connectivity matrix. So we did form in our MATLAB code. We did see how we can do it using write a logic or an algorithm for that. So I think that's straightforward. No, not so straightforward, but we did some exercises for that in when we discussed 1D appearance. So we'll just quickly do this. So if we are defining a global matrix, so first of all you should have, so since total global nodes are four, you'll have four rows and four columns. So we'll just start with 3 3. We'll start with K33. So K33 would have contribution from how many elements? I'll just do it. So K33 would have three is in there in both elements, so it should have contribution from element one also. So sorry K11, and for element one, the global node 3 is present in the second local node, and for element 2 it is present at the first local node. And likewise, if you want to do uh, 2 3, 2 3 is present only in element 1, so it should be from element 1, and it's 2 local 2 is global 2 is local 1, and global 3 is local 2, so it should have contribution from the K12 element of element 1, right? So that's how we did last time earlier also. And then after assembly, we have our final global metrics, global stiffness matrix and global force vector. So after that, we just need to apply the boundary condition, and that is simply the way that we did in 1D. So we just need to know the uh, data of the nodes wherever the related boundary condition is specified, and we just replace we just eliminate the rows and columns and modify the K and F matrix in the same way. So one thing different here in 2D compared to 1D is the a new kind of error is there. So in so FEMA is an approximation method. So there will be some error in the solution, but in 1D there will be some error, but that's same in 2D. But in 2D there's a different kind of error that's not present in 1D. That is a discretization error. So the discretization error, there is the inaccuracy in mapping the domain. So any idea how can we reduce the discretization error? Anyone, any guesses? So to reduce the discretization error, we can refine the our mesh. So if we have some curve geometry here, if we want to map this part with only one element, we have to go like this. So now we have this area which we have missed. But if we map it with two triangles like this, then the area left is reduced. So uh, discretization with a more refined mesh or large number of elements, we can reduce this error of discretization. Okay, so yeah, next thing is which we didn't considered earlier is the mapping of the triangle elements to a standard coordinate system or the natural coordinate system. So that we did in 1D also. So in 1D it was pretty straightforward. We just had single simple linear element or simple line element which had some coordinate, random coordinate x1 x2. We just had to move it to standard coordinate -1 to +1. So it was the simple approximation, sorry, simple transformation. And now for triangular elements, we have to map it to a master element, which looks something like this. So it should be a right triangle, which should have vertices 0, 0, 1, 0, and 0, 1. So now again the steps are similar. We are using linear mapping. So we for to get the mapping function we have to express the x and y coordinates of the physical space to the zeta and eta coordinates of the natural coordinate system. Then we substitute it and we get some function in terms of these eta and zeta. This like we got it for x, we'll get the same for y. And if we'll arrange it like this, x equals to xi into ni, we can see that we will directly get the shape functions here, all the approximation function. So okay, yeah, that's how we do the mapping here to the natural coordinate system. Now, when we are changing our domain from the given physical space to the natural coordinate system, we'll have to change our integral and all the derivatives involved. So, uh, so here again, like we used to use the Jacobian for that. Similarly, we'll need a Jacobian here as well. So earlier the Jacobian used to be just dou x by dou zeta. Sorry, dou zeta by dou x, I guess. Yeah, but yeah, sorry, dou x by dou zeta. So now since it's 2D, there will be instead of a single value, there will be a matrix of four different values involved. So if we are given a derivative like this, so if we want to transform it, we'll have to if we want to transform to eta zeta coordinates, we'll have to use this. Okay, so that's how we use Jacobian. I think it will be more clear when we do some problems, when we actually solve some problem based on this. Okay, so I just simply yeah, simplified this a little. So if we are given our uh, the given integral of our this stiffness matrix, this is usually in this form here. So it's given in x and y. If we want to change it to eta and zeta, we just have to introduce this inverse of Jacobian. So yeah, I think yeah, this is it for what we did in week 7, and we'll move on to the problem solving part. If anyone has any doubt, we can discuss that now. Okay, so if there's any doubt, we can discuss it now, or we'll move on to the next problem. Okay, so we start with the first problem. So, are the following polynomials complete or not? So, yeah, can someone answer this? We start with first part, 5 plus 2x. Yeah. So it's not an MCQ actually. So you'll have to answer for each. Okay, you are answering for which are complete. Yeah, 5 plus 2x is complete if it's 1D. Yes, and no if 2D. Then it won't be considered complete. And B part, is it complete or not? Yeah, B and C are not complete. And D again, we said this is complete. Okay. Okay, so show that the following matrix is non-invertible by row operations. Verify using determinant. So when is a matrix non-invertible? When determinant is zero, right? And what other condition do we see? Result is zero. You mean to the determinant, right? If determinant is zero, if rows are linearly dependent, any row is linearly dependent, or if rank is less than the size of matrix. So, so according to second condition, if we show that the rows are linearly dependent, so if we can just show that any row is can be formed by a linear combination of other two rows, we can say that it is non-invertible, right? Can we do that? So if you see the row one, if you multiply row one by 5 and add row 2 to it, what you will get? So, or we can just do one thing. We apply row operation on row 3, that we make row 3 minus 5 times row 1 plus row 2. You see that 5 times 1 plus 0 would be 5, and 5 minus 5 would be 0. So the matrix becomes 1 1 5 0 2 1, and this becomes 0, and then again 5 times 1 would be 5 plus 2 7, 7 minus 7 is 0, and again 5 times 5 would be 25 plus 1 26, minus 26 would be 0. So you see that the whole row is eliminated, so all element of row becomes 0, so that means that its determinant would be 0. So this implies that its rank is 2, which is less than the size of matrix. This means it is non-invertible. And you can just simply check by determinant also. We have 52 minus 7 is 45, minus 5, sorry, this should have been minus 5. We'll get 0 here. So hence this is a non-invertible matrix. Okay, so this here is an interesting exercise. So far, for triangular elements, we saw that if we get the nodal coordinate values, we can form a matrix A based on these nodes, and if we take the inverse uh, of that matrix, we'll get our approximation function, the coefficient of the approximation function. There's one more way that we can do that. I think we discussed that way when we're doing 1D FEM. So we'll try to see to use that also and see if we get the solution, get the approximate function. So find the linear interpolation function for triangle whose vertices are 0, 0, 1, 0, and 0, 1. So we'll take a pretty simple triangle here. So its vertices are 0, 0, 1, 0, and 0, 1. So we'll take this as node 1, 2, and 3. Okay, so anyone can suggest me how do we start? How do we solve this? So first of all, we approximate the solution u. So since we are approximating a linear solution, we have it as and what is the other way we can write the solution? Is this correct? Yeah, if we are assuming a linear approximation of the solution, we can write it as a linear polynomial, right? A naught plus a1x plus a2y. So I'm asking what other way can we represent the solution also. So if you remember, in terms of approximation function, also we can write it as u1 psi1 plus u2 psi2 plus u3 psi3, right? Okay. So now, if we substitute the value for node 1, what equation do we get? So at right hand side, our psi1 should be equal to 1, psi2 should be equal to 0, psi3 should be 0. So at right hand side, we'll get u1, and on the left side, we should have a naught. Since x is 0 and y is 0, we'll only have a naught. Then we substitute value at node 2. So at right hand side, we should have u2, and then a naught. Since x is 1, we'll have a1 and y is 0. Then we substitute node 3. We have u3 here, and we have a naught plus a2, right? Okay, so a naught yeah, a naught a1 a2 are unknowns here. So if we combine these equations as in 1 0 0 1 1 0 1 0 1. So we can write this equation in this form. And if we take the inverse of this and multiply that side, we'll get our a naught a1 a2 that are unknown, right? So once we get a naught a1 a2, we substitute back into the above equation, and we arrange it in like whatever what we have right side here, as we did it for 1D FEM also. So this will give us our psi1, psi2, psi3. So we'll not go with taking the inverse of this matrix. That is a tedious task, but you can just solve for u1 a1 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 a2 simply. So we have directly a naught equals to u1, a1 equals to u2 minus u1, and a3 equals to u3 minus u1, right? So now we substitute back here. So we have u1 plus u2 minus u1 x plus u3 minus u1 y. And if we arrange in terms of u1, u2, we have u1 1 minus x minus y plus u2 x plus u3 y. So we have our approximation function psi1 as 1 minus x minus y, approximation function psi2 is x, and psi3 is y. So this is how we get our approximation function here. So if you remember, I think you should have you would have done this in the lectures also. Uh, since this is our standard triangle, so we are getting a standard approximation function, right? But this can be applied to any kind of random triangle, and you'll get the approximation function. The only thing that you should have, you should, yeah, yes, sir. You raised your hand.
My system is not working fine, sir. Sorry.
Okay, no problem. Yeah, so the only clause here is that when you're whatever element you are having here, it's based on its coordinate, whatever matrix that you're getting, this one here, it should be invertible. If it's non-invertible, you can't find the approximation functions. So that is why when we're choosing the elements for FEM in 2D, there are certain restrictions on the elements. For example, you can't have a very thin element like this. So since its area is all very close to zero, it's the matrix found by this element would have a determinant very close to zero. So it would be very difficult taking inverse of it. So in your computer program, it will give some convergence issues when you're taking its inverse. So that's why this kind of trying elements, and even I think if you're when you're dealing with the four noded to five noded elements, their concave shape is not allowed like this. Can't have an element like this. If no, this is a node. This is a node. This is a node. So these kind of elements are also not allowed. That is the same. The matrix formed by these would give you a would give you a non-invertible matrix. So yeah, that's why there are certain restrictions on the type of element that we can use. I hope this was clear here. Okay. Now, which two-dimensional element is suitable for developing interpolation function for displacement u in the form c1 plus c2x plus c3y plus c4xy? Any idea? Quadrilateral, right? Why quadrilateral?
Yeah, got it.
Why is it? Why quadrilateral? Yeah, that's right. Quadrilateral, but why quadrilateral? This is because we have, yeah, four nodes in there, and we have four unknowns here.
That passes triangle is there, no? It covers that for.
Yes, yes, right. So simply, if this kind of approximation has four unknowns, so
Yes, sir.
would need four nodes for that. Okay. Okay. So consider 3 by 3 matrices given the options. Which of the options consists of a matrix which is with linearly independent rows and columns? That is, it is invertible. Which of these matrices is invertible? think I have added rather complicated metrics here. First option. Okay. Anyone has any other answer? Uh, D is also proposed. The first option has determined zero, so it would be yeah, it would be non-invertible, right? It will have linearly dependent rows. That's not the answer. D, I think, is right. So I think D is the answer for this. We'll try to find the determinant of D. We have 12 minus 42 plus 0. Oh, 30. 0. D is not the answer. We'll check for C maybe. So we have 2 times this is 39, I guess. One. This is minus 75. This, I don't think this would go to 0. Let me check. This is 78. Yeah, this is not equal to 0. I think C is the answer. Check for B also. It appears. I guess check for B also. I hope I did it right. Yeah, this is also not 0. So this is also right. Okay. So I hope I did it correct. If there's anything, let me know. Okay, so move on to the next problem. Okay, so we have to describe the given domain into four elements. First using triangular elements, and then next using quadrilateral elements. And then we have to write the element connectivity for each of the cases. So we can first start by triangular elements. We can just do it here, right here. Getting triangular elements, we just need to draw two diagonals. We'll have four triangular elements. We do the global matrix numbering as this 1, 2, 3, 4. We'll keep the same for both. And then, so we'll start numbering the elements 1, 2, 3, 4. Then local node number inside 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I forgot this is fifth node here. So connectivity matrix here is so first of all, how many rows and how many columns in the connectivity matrix? Four rows, right? Because we have four elements. And then we have three columns because we have three local nodes. So what is the first row? 1, 2, 5. That is right. 1, 2, 5. Second row, 2, 3, 5. Definitely right. Then third row is 3, 4, 5. And then finally fourth row is 4, 1, 5. Right. Okay. By the way, general mesh file for complex geometry. Right. Demonstrate how to generate mesh file for complex geometry. Is it necessary to use GMesh software for generating element connectivity metrics? Yeah, that is actually right. It's not just GMesh, there are multiple software that can do this for you. And in fact, for some standard domains, you can write your own code also. It's possible for certain standard domains. But for rather complicated geometry, it's much easier to do it using GMesh. If you want, I can demonstrate a bit. I can do that. If everyone agrees, should I show a little bit of GMesh to you? What does everyone else think? I hope I have Gmail installed. Let me check. What does everyone else thinks? Do you want me to demonstrate a little bit of Gmesh? What I can do is I happen to have a Python code also, which can read your mesh file in Gmesh and generate the connectivity matrix and all that. Let me see if I can get it to run. Sure, sure, I can. Let me see where that file is. I hope no one has problem with this. So let me share my screen here. Can you see this Gmesh window? Yeah. So we create a new file here. So it asks if you want to use GeoX, and we will continue with that. So I'll make a some basic geometry. I'll start by adding point. So can you see this dialog box over here? I don't think that's visible because only one window is being shared. Let me see. Try again. Yeah. Wait. Let me reshare my screen so you can see the dialog box also. Yeah. Now can you see the screen? Yeah. Now you can see the dialog box, right? So I am adding a point here. So I'll just add a point here, 0, 0, 0. And this fourth point, this fourth input is for the prescribed mesh size at that point. So by default, we keep it one. But if you want at some point mesh to be smaller or larger, we change that for that particular point. So now we'll keep it to one. We add the point. We add the next point, 1, 0. Add it. We add 1, 1. Add. We add 0, 1. Add. So we added 4 points here. Now we press Q. do about it. Then we add line, select first point, then select second point. Then first point, second point, first point, second, second point, first point, then second point. We got a line here. We press Q again. Now next we define a plane surface. Let the surface boundary. If there's supposed to be any hole in the surface, we have to select the hole, but we don't have any hole here, so we press E. So you see these symbol here, these arrows coming up here. That means this is now a surface. So next thing is you have your domain ready now. If you want, you can also add uh, physi- physical identity to these different boundaries. Uh, for applying boundary conditions, this is essential in your code. So anyways, we don't need it now. So what we do is just we create a mesh. You see, a mesh is created, four triangles here. Now we save this mesh. Export. I'll save it as trial1.msh. We have a message here. Yeah, trial1.msh. Save. Version as key4. That's it. The mesh is ready. Now I'll show you the file. So this is the mesh file that is created. So initially it will tell you the format. So we had chosen version 4 as Sky, then ending of that part. Now it gives the entities. Entities I don't remember. I usually work with version 2 as Sky. There it doesn't show entities. We'll skip this for now. And then we have nodes. So this is your node data. It's a little complicated for me. Node data. I don't remember seeing all that. I'll try with version 2 SQ. Yeah, this is much simpler, cleaner. So we have the format written in the version format, and then we have the node data. So after node data, the first thing you see is this the number of total nodes. So you see we have four triangle, so we have total five nodes here, and then we have your coordinates of the node. So we have total five nodes here. So coordinate data for each of the five node is here. You see this is obviously looks what you saw in that figure, right? And after node data, you have the element data. This element data is your actual element connectivity metrics. It will give you that. So initially there's some I don't know line element data or what, but wherever you have this two here, this starts your actual triangular elements. So the last three columns of this, each two row, is your connectivity matrix. 251. I think five is your middle node. So five will come everywhere. 251, 154, 352, 453. So this is how you create a mesh file. And generally there are solvers who can directly read this mesh file, so you don't need to worry much about all this extra data, how to uh, what that mean, how to use that. Usually the solvers would do that directly for you, but if you want to write your own solver to read this file, then it's a little tricky. You will have to do it yourself. You should know each and every quantity, what is the function of that. So this is how I generated the mesh, and I have a. Let me see if I have the code with me. Yeah. So this is the code that I had written to read this mesh file 1a. So I'll show you that file 1a. This is a mesh file that had 902 nodes. All the node data is here. Then after that you had the element connectivity data. So this, using this code, I had filtered out all this data to finally, let me see if it is still running. We can print out the data. Yeah, you see, that's big data. Won't be easy to understand. So in this program, what I did was I read this mesh file, sorry, and got the node first nodal data. This is where I printed nodes. This is node data, and then next is the connectivity metric, which I have stored in this elements matrix. And then next part of this code, I had written down this data into a VTK file. So there's certain format, VTK format. Uh, so if I write in that format, I can read this VTK file to get the geometry. I don't know if I still have it. Let's show you here. Wait, just a minute. Yeah, so this was this mesh actually, and you see there's some approximation error going on here. Circle. So yeah, this is my output of this mesh. What I wrote in a VTK file. So that VTK file I could read in Paravi. Okay, so I hope that's all I did for generating mesh and reading them. If there's any doubt, you can still ask me. How can we import in MATLAB? It's simply the way the way I did in Python. You just have to write the same thing in MATLAB. You just read your mesh file in MATLAB and do that. Okay, so yeah, I'll share my screen again here. Wait a minute. Okay, so this is the simple job that we did here for this same type of domain that I created in Gmesh, and we had to write a rather complicated code there. But yeah, it's easier when geometry gets really complicated and the data is huge. Okay, yeah. Now we also had to discretize this using quadrilateral elements. We again have this. So now we have to create four quadrilateral elements. We have this and this. This makes four quadrilaterals. Now we have rather a large number of nodes. Okay, so again we have four elements, so we'll have four rows. And now we have four local nodes, so now we have four columns. So now element 1 would be, row 1 would be, so element 1, 1, 2, 3, 4 is 1, 5, 9, 8, right? For element 2, it would be 5, 2, 6, 9. Then element 3, it would be 9, 6, 3, 7. And element 4, it would be 8, 9, 7, 4. Okay, I hope this is correct. Okay, I hope yeah, this was clear. Now find the interpolation functions for the quadrilateral connected by the points 0, 0, 5, 0, 5, 3, 0, 3. Now we'll have a little challenging geometry. We have 0, 0, 5, 0, 5, 3, 0, 3. Node 1, node 2, node 3, node 4. So how do we go about? Yeah, that's right. We write the approximation as now with four unknowns: bx plus cy plus bxy. And this can also be written as u1 psi1 plus u2 psi2 u3 psi3 plus u4 psi4. Again we follow the same steps. If there's any geometry, if you just follow the same steps, you can get the approximation function, shape function for that. In fact, I think in class sir did by approximating xc there for the mapping. That can also be done. Same thing. So now at 1 we have u1 equals, right, with that first. So we have both x and y 0, so we'll be having only a, and right side we have u1. At node 2 we have uh, a plus we have x equals to 5 plus 5b, and then y is 0, so next two terms would be 0. Right side we'll have 2. Then at node 3 we have a is there plus we have both x and y, so we have 5x plus 3y plus 15xy equals 3. Then at node 4 we have a plus, oh, it's not, Oh, I have made a mistake here. It's not xy, it's AB. So it's 5B, 3C plus 15D. That equals to U3. Okay, I hope this is right. Then at node 4 we have A plus x is 0, so we will have only 3C equals U4. So if we assemble these equations, we'll have 1, 0, 0, 0, 1, 5, 0, 0, 1, 5, 3, 15, 1, 0, 3, 0. A, B, C, D equals U1, U2, U3, U4. Okay, so again we need to find A, B, C, D in terms of U1, U2, U3, 4. We substitute back in equation, first equation, and we get our approximation functions. I think this is also similar to what we studied in the lectures. That this matrix is nothing but 1 x1 y1 x1 y1 1 x2 y2 x2 y2, like that for the four nodes. It's similar to what we got there. So we take its inverse and we find the our ABCD, or else we can directly just solve this as a a is equals to u1, so b equals to u2 minus u1 by 5, c equals to yeah c equals to u4 minus u1 by 5, and d is would be 15d equals to u3 minus u1, 5b would be u2 minus u1, and 3c would be 3 u4 minus u1. So d equals to u3 minus u4 minus u2 minus u4 plus u1 upon 50. Or we can also write this more creative way. This is u1 minus u2 plus u3 minus u4 upon 50. So substitute back in first equation, we have u equals to a c1, sorry, a is u1 plus bx u2 minus u1 by 5x. plus C is U4 minus U1, and D is U3 minus U4 upon 15 XY. 1 minus 1 by 5x, or x by 5, so this is by minus y by 3 plus x by y 50. Then U2 is x by 5 minus x by y, xy by 50 plus, what is the coefficient of U3? Xy by 50. And then for U4 we have y by 3 and is xy by 50. I hope there is no sign issue here. So you see, this would be our first approximation function, second, third, and fourth. Okay. I hope this is clear. If there's any doubt, you can ask. All right. If there's no doubt, we can move forward. Okay. So this time we have a different triangle, so we can check that. Find a linear interpolation function for the triangle whose vertices are. We have 0, 0. We'll just quickly go through this. You know how to make the matrix, right? 1, 0, and 1, 1. This is a different triangular time. So how do we used to make the matrix? 1 x1 y1 0 0, then 1 x2 y2 1 0, then coefficient of u4. Okay, u4 is y by 3 minus xy by 15. That's right. I made a mistake here. Okay, that was it, right? Yeah, that's what I was thinking. Thank you. Thanks a lot for pointing this out. Okay, so now we want to find the interpolation function for this triangular element, this triangle. So this is different from our standard triangle now. So what we used to do is we used to uh, form a function and substitute the value of each node and form the equations, and then form our matrix here, right? Instead of that, we'll just do it directly here by that same formula. So the rows of this matrix should be 1 x1 y1 x1 y1 1 x2 y2 1 x3 y3. So that's what we are doing: 1 0 0 1 1 0 and 1 1 1. Then this here is our unknowns a b c, that is the coefficient of the approximation function. And here we have on right hand side the solution value u1 u2 u3 addition of the nodes. So we have to find a b and c in terms of u1 u2 u3. We get, so it's quite straightforward to solve. A is equals to u1, a plus b equals to u2, so b equals to u2 minus u1, and c equals to uh, so a plus b plus c equals to u3, so c equals to u3 minus u2 minus u1. I hope I did that right. Just correct me if I'm doing anything wrong. So our approximation function would be a plus bx plus cy. Okay, so we write this. We get the coefficient of u1, that this is 1 minus x minus y. Then for u2 we have x minus y, and for u3 we have dy, I hope. Yes, so this would be our first approximation function, second approximation function, third approximation function. Oh, u3 is not repeated anyway. Yeah. So you see, for this kind of triangle, this triangular element, we get different approximation functions. I hope there's no doubt here. This would take some time. But we know the approximation function, right? Let's see if we can do on the problem. This is a rather interesting problem. I think instead of doing this, since we have limited time, we'll do this first. So we have an element whose e- triangular element in which the equation of line are given. So uh, how do we find this equation? Sorry, the approximation, the shape function for this kind of element. Anyone, any guesses? Find the interpolation function at node 1 for the 3 node equivalent triangle element shown in figure, this figure. If we'll get time, we'll try to find for others also. So we need to find psi1 here as a function of xi. Anyone, any guesses? Okay, so we'll start with the given uh, equation of line 2, 3. So it's right. This is the equation of this line. Suppose I define some function as this. So if you see, I took this this left hand side to right hand side. So if you do that, what you'll have is this minus this equals to 0, right? So I am defining this function, which is which which is valid for this line here, and it will always be 0 for at this point, right? And that is the property of the approximation function, that it should give 0 at these two nodes, right? So I can write my approximation function for 1 as some alpha times eta minus root 3 1 minus I. Okay, now I just need to find the value of alpha. So the given coordinate system of eta and zeta, we can see that origin is here at this point. This point 2 is 1 0. This is minus 1 0, and this point 3 is 0. So we substitute the value at node 1. So what should we get at node 1? At 0 0 equals to 1. 0 0 is this point right here. This is 0 0. So this is not any node, so it won't be of any help to us. So instead we can substitute this function at node 1, where which is at minus 1 0. So at node 1, this psi 1 should be equal to 1, and here we have eta is 0 minus root 3 into 1 minus 1 minus minus 1, that will be 1 plus 1. So your alpha is equals to minus 1 upon 2 root 3. I hope. Okay. So your psi 1 turns out to be root 3 1 minus xi minus eta upon 2 root 3. Right. So this is how you get psi 1. So in the same way, you can find the shape function on the other two nodes, right? You just need to know the equation of the line opposite to that node. So likewise, you can define psi 2 as some beta times the other equation of line, eta minus root 3 1 plus psi. Okay, you substitute the value at node 2, you will get 1 equals to node 2 is 1 0. You can get the same thing, same value. Beta is also equals to minus 1 by 2 root 3. So your side 2 would be, okay, and same way you can find side 3 also. So what should be the equation of the line opposite to node 3? Any guesses? So what is the equation of this line here? This line is actually eta equals 0, right? So you have, this is gamma into eta. Substitute node 3, we have 1 equals to, here your eta is root 3 gamma. So gamma equals 1 by root 3. Your side 3 is equals to eta by root 3. Great. So these are the three approximation function for this triangle here. So I think, yeah, we are almost out of time now. If there's any doubt, you can ask. Otherwise, we can conclude the session. Also, I would like to just mention that, okay, for reading Gmesh file. Okay, can you drop me your email ID, or if you know my email ID, can you just send me an email? I'll share the code there with you. Okay, I'll just write it somewhere. Anyway, nice, right. Okay, so one more thing I would like to mention that since I was unable to take last two sessions, so I for that makeup one session I already took on this last Sunday, and another makeup session I'll take on the next Sunday, Sunday 4 to 6. Okay, then I think we can continue the session now. Thank you so much for joining. I'll see you again on the coming Sunday. Thank you so much. Bye.